Welcome back to class 3. In the first video, which is too long, really it was just setting up stuff, really mostly for the next class because we didn't want to cram it all into that one class. So now we're moving on to this topic today is rectangular coordinates, and one problem that's very common in rectangular coordinates that we'll see is projectile motion. And as I had mentioned before, this is probably stuff that you did in physics, probably even in like middle school. You probably had some class where they introduced these. So what we're dealing with now is we have this x and this y, and from the derivative discussion of them, we note that they're somewhat independent of each other. The motion in the x direction is somewhat independent of the y direction. Now, it's not completely independent. We'll see there is something that sticks them together. But we can think of projectile motion, which we notice there's an arc. That's a really important thing. There's an arc taking place. That we have motion that's in the y direction is just gravity, right? It's just something. It's a constant acceleration problem in a single dimension in the y direction, and that acceleration is downwards gravity. And in the x direction is actually a constant velocity relationship, right? So the initial velocity is the final velocity in the x direction. We're assuming that there's no like wind resistance or aerodynamic drag taking place, which is, for velocities that aren't, real high, that's a fairly okay approximation. So you can almost think of, and I like this little cart idea, that you're maybe on a cart and you're throwing the ball up in the air and then watching it land. But because if the cart's moving, it has an x direction, so that's actually going in an angle and coming up. And so you could think of, well, if you were to take only the y direction and you were just going to throw the ball up with the same initial velocity as the one that you were shooting over there, they would both land at the same time, right? If you just throw the ball up with the same velocity as the y component of the one that's at an angle, they just go weep, boom, right? So you just think of two things happening at the same time. One is a, acceleration problem, and one's just a constant velocity problem, right? And they look like this. And so what would they look like if you, and I say they're independent, but they're not completely independent because they're both related by time, right? So time links them together. So it's not just completely independent actions. It's that their position is dependent on time. So you might ask yourself, well, what does this look like if you combine the two? And so all right, so the answer to this is time. By the way, what connects the horizontal and vertical equations is time. And if you were to combine these two, which is they're up right here, one thing that's going to make this easier to do. Did I do it? No, I kept it in there. Okay. A lot of times it's easy to assume that this position is 0, right? Or maybe even this position is 0, right? We might want to pick out where it starts and say, okay, that's where we're going to place our coordinate system. So it depends, right? But let's just keep it in there as a generic thing. It makes it look a little bit it looks a little bit easier, right? So if you take x is equal to x naught plus, and I keep forgetting which I put on the outside. I put the O on the x outside, right? So here is the initial velocity in the x direction. Of course, well, let's say that it has a velocity right here, or its initial velocity, I should say, is vx not I plus vy not j, where vx is equal to v magnitude of v times the cosine of some angle. We'll say that it's got some initial angle that we'll call theta often, somewhere in there, and that vy is going to be equal to the magnitude times the sine of theta right there. Just remember that. And then if it's also the initial one, right, so we could say right there, say, boom, we'll put that initial thing in there, right? So the magnitudes of those, right? And so anyway, we have this initial velocity that we could get if we have this known initial velocity. We get the x direction component of the thing. Solve for time, and that's going to be the change in position, right there, moving that guy over and dividing through, divided by v of x naught. Well, let's put that inside here. Let's replace t with that. And this is, okay, and if you do that, you end up with y is equal to y naught plus v y, right? So I have that, yep, I wrote it that way, times x minus x naught divided by v x naught minus 1/2 g, and then x minus x naught divided by v x naught, all that, the whole thing squared. Now, what we'll often do, I think I might do it in an example. It would be nice to do it right here, because this really kind of describes it. It might not be revealed right here yet, but this is a parabola, right? Because let's take, okay, so if we assume, so I'm going to make a little bit of an assumption, x naught, let's see, excuse me, yeah, is that right? Yeah, x naught, it's just x naught, don't need parentheses on it. Assume x naught is 0, right? It's just a good place. Why not? We don't always treat that, because it might be better to, if somebody's going to shoot off of like maybe a cliff and then land down somewhere. It's nice to have the y at the bottom of the ground level underneath the cliff, because so we don't have negative y, right? But we will often take this right here as being 0. And if we can also replace these ideas right here, right? So then we can say, why not right there? Note plus, let's put this guy in here, the initial velocity. I don't want to write all of it out. Yeah, I guess I will. Times the sine of theta, right? And then we have underneath right there, we have the initial velocity times the cosine of theta. And this is going to be times x, because I said assuming x is 0, so it's going to be times x right there. Notably, these cancel out, and then these turn into the tangent of theta minus 1/2 g, okay? And like I said, I'm going to take x as 0 right here. So, and then I'm going to have, and I'm going to replace this guy with this guy right here. So maybe I will go, maybe to make him look better, to make all of this look better, maybe I'll go g over 2 times v naught squared times cosine squared of theta, right? Because I have this right here inside the square, so I'm taking this and I'm squaring it, and then I also have x minus x naught squared, but I went ahead and assumed this right here, so we just now have x squared right there. So what you end up finding, let me rewrite it a little just underneath the thing. If you want to find the vertical position of something, you take the original position and you add the tangent of theta times x minus, and this, you get all this happiness right here, g over 2, I'm going to scrunch it all in here, v naught squared, right, the magnitude of the initial velocity squared cosine squared of theta times x squared. And I think I got that right because I don't have it written down on my page right there, but it's something that we do often. And you'll see that we have y as a function of x, right? This is a constant, that's a constant. These are all known things right here. So this is just y as a function of x, which describes a parabola. So we have parabolic motion is what we end up expecting, right? And just like we saw right here, it's supposed to be a parabola, even though it's, maybe it doesn't look exactly like a parabola right here. And so this is kind of a useful concept to keep going back to when approaching. I mean, you might there will be lots of problems where this is good enough, right? Just getting to this point right here is going to be good enough. And I don't give this on the equation sheet, by the way. I only give you these. So be aware to be able to do this, because we might have other scenarios where this concept comes up again. So I want you to be able to do that. Another a thing that is true, kinematic equation that is true for projectile motion, is in the y direction. We can also use this this where we have the when we're dealing with something where we have a constant acceleration and acceleration. We want to have a relationship. See if I can try to say this right now. This right here is the consequence of the acceleration that's like this, right? dv, and we'll call it dv dy, right? If we work this out as we did in class 2, we end up with this equation right here, and this also remains true and can be useful to us. Most of the time when this is useful is when we perhaps want to find the location of the peak, right? So it's going to peak when the velocity in the y direction is 0, right? That's when it goes its highest, remember, because we're throwing the thing up in the air. It gets to a certain height, stops, and then starts coming down. So when if we set this equal to 0, and this is the initial velocity right here, we can find the y of how high it goes. So this can sometimes be a useful equation to us. I think that's pretty much all I had for this video right here. I did say that there's Mechanics Interactives from the publisher, McGraw Hill, and you might want to try out some of these. I have the links put up in a Blackboard. I thought about having some type of activity in class where we attempted to do this, but this class just has too much stuff in it to be able to maybe use up with one of the ones in-class activities. But let's see what's coming up the next thing. Do I do an example? Yes, I do an example. Okay, so in the next video we'll do this problem. All right. Once again, too much introductory stuff. 13 minutes. Gotta narrow that down. All right.